So this talk is going to be an overview of some of the work we've done in the past, like a year or 2 years. I'm trying to make it non-technical, and you can stop me for questions. So this is based on drawing works Sharma, Jay, Vanu, and Emmett. And we're going to talk about feature extractions for universal hypothesis testing problem via run constraint optimization. And one motivating application is anomaly detection. So what happens with anomaly detection is you want to detect the abnormal behavior of a system. For example, the onset of cascading failure in the power grid. And it's based on a limited running data of system. So basically, you observe what is currently running. I want to say whether you're going to have a blackout on the right-hand side or you're going to be OK. So in the application we are looking at, it has the following property. First, you have a lot of history data for the normal behavior, okay? And the system could exhibit a variety of abnormal behaviors, and the data about that is limited, okay? And you can formulate this problem as a hypothesis testing problem. Basically, you are given a sequence of observations. Well, you can assume IID in this talk, and we have two hypotheses. First one, for the normal behavior, let's right now stick to just a simple hypothesis. So we have Z1 that's distributed as pi 0. For anomaly, you have Zi distributed as pi, which belongs to a set of distributions. And this set can be known, you have to learn, okay? And we want to design the test. Basically taking this sequence of observations and give a binary value. If it's 0, then you say it's OK, it's a normal. If it's 1, then you claim anomaly. Okay? And the performance evaluate is basically the false alarm. Basically, what happens if the truth is pi 0, but you claim it's 1? That's a false alarm, and the other is probably of misdetection. And we restrict to tests that are a function of empirical distributions. You can always do that with a loss of generality for the IID case. OK, so let's look at this problem from geometric view. So let's look at this space in the probability of simplex. Okay, and pi 0 is the abnormal behavior, which is point here. And as I said, the abnormal behavior would be a lot of different cases here. Okay. Well, if you look at this picture, so if you want to design a test, the natural idea is just draw something around this pi 0. Okay, and you say, well, I draw a ball. If what I observed, the empirical distribution, is inside the ball, then I claim it's normal. If it's outside the ball, then it's abnormal. Okay, that's one of the simple ideas you can come up with. And just remind you, in this picture, we are looking at the probability simplex. Okay. So actually, if you take this ball to the divergence neighborhood, then this gives you the Hofstadter test. Okay? So it's defined as using a KL divergence, which I guess most of us are familiar with. So basically, expectation of the log likelihood ratio between mu and pi. Okay, and I will use this notation to denote the expectation in the following slides. And what we know about Hofstadter test? We know it's a symptotic optimal. Basically, what I mean by that is, if you look, the probability error will decay exponentially according to the number of samples. And you have two error exponents, eta and beta. For Hofstadter test, for given error exponent eta, you achieve the largest possible decay rate on the other probability error. So basically, what I'm saying here is that Hofstadter test is optimal, but it has a drawback. Okay, so it has a drawback when the size of the alphabet is large. What do I mean by size of alphabet? It's this pi 0, remember, it's the amplitude distribution of a sequence of data. And this data has to lie in some space. Here, we're looking at a finite set. And to make this concrete, what it means, if you look at the probability of false alarm, the actual behavior, you have to look at what's before the error exponential decay term. So it's n to the size alpha bit, which is the power of n. So you can see if this z is huge, then you have a problem with your test. Okay. So this you can either study this issue from the variance of this test statistics, or you can look at this from the biotics. Yes.
Z is that Z the same as the space of Z and so?
Oh, okay. So this is basically the sequence. And this is the space where the set of sequence lies in. So, for example, take if you look at a finite alphabet, then it's just 0 to say some number z. Or
so modulus of Z is the dimension of Z?
no, this is a finite set, so it's the cardinality.
Okay.
Thanks. Well, if you're looking at infinite dimensional stuff, well, we'll get that later. So the outline of this talk is first atop this drawback Hofting test, and we're going to look at mismatch test, which is basically a feature-based approximation of the Hofting test, and then we look at techniques to extract features. Okay. So, hello? Okay, thanks. So I just show you a picture of this Hofting test, okay? And our idea is to approximate the divergence spot using these spotting hyperplanes. So in this case, the simple case is that you approximate spot just using two hyperplanes, which are parallel to each other. Okay, that's one approximation you can do. Or you can use more hyperplanes, or you get more. And this gives you the mismatch test. If you look at the KL divergence, it's defined. It has a variational representation. Basically, you can write it as a supremum, or the expression of f under mu minus the log moment generating function. The key part is this f is over all possible functions such that this is well defined. Okay. And for mismatch divergence, what you do is you restrict this function to a small function class. Okay. In this picture, basically, I'm restricting myself to those two hyperplanes. Okay. So you can think of each f, it corresponds to a hyperplane in this space. And basically, I'm restricting myself here to a linear function class. Okay, so this gives you an approximation of this KR divergence. And this function class, what's considered here is a finite dimensional function class. And the mismatch test is basically if you look at the point lies in this approximation or not. Okay, and what's the performance of the mismatch test? So now, if you look at the arc exponent, of course, there's a trade-off between these two types of arc exponent. But the pre-arc exponent, the term before that, now it's a power of n, and the power is actually the dimension of the function class. Well, in the Hofting test, it's the size of the alphabet. Okay, so I'm addressing the issue here, and if I can choose a function class that's small enough, and I get still a pretty good approximation to this divergence spot, then I'm okay. So we address this dimension issue here. But yes. Sure.
So, and the eta doesn't change?
Good. The next slides. Thank you. So, but the average one is usually worse, unless it's a perfect approximation. There's no free lunch. So there's a trade-off between these two. So when you use approximation, then the other type of exponent is smaller than the optimum one. So the question is how you can choose the function class to make a good trade-off between these two. Okay. Well, this actually depends how you choose function class. Remember, this only depends on dimension of function class, but this depends on actual function class. Okay. So of course, the natural question is how do you choose this function class? And this brings us to the problem of feature correction. So let's set up the problem this way. Given some distributions that sample from pi 1, basically abnormal behaviors, and given upper bound d on dimensional function class, which guarantees your performance on the term before the error exponent, how do you choose the best function class? Okay. Well, there's various criteria you can use. Let's take one way. So for given upper bound on the worst case of type, basically missed detection, maximum error exponent for the false alarm probability. Okay, that's one way you can pose the problem. And you can return this as a maximization problem. Basically, you look at the worst case false alarm error exponent and maximize the function class for that. But there's a constraint. Basically, you want the dimension of function as small than d. And this constraint is what gave us trouble. So it can be cast as a run constraint optimization problem. And this dimension of the function class becomes the run constraint on X. Okay. Well, if you can solve the problem, then you get the best function class you have. But right now, we don't have a complete answer to that. What we know is that for special rank 1 case, I can find a global optimal solution. But for general rank 1 case, it becomes a combinatorial problem. And right now, for the other general case, we just use a heuristic, which is a gradient descent plus projection. Okay, this is similar to the SVP single valued projection algorithm. Well, you can prove it's guaranteed to find local optimal solution. Okay, so let me give an example of how this will work. Sure.
Why bother with this combinatorial optimization problem? Did you try using the nuclear norm instead?
Good point. So I tried several ways to use nuclear norm, but this function itself is, so usually in matrix computation, it's a quadratic objective function. Here, when I plug in with the nuclear norm, it doesn't give me a low rank solution. So I'm still trying to way to tweak that nuclear norm to have a low rank solution, but haven't succeeded so far. The trouble is it doesn't give me a low rank solution. No.
When you relax the constraint, you under certain conditions, you have performance guarantees that are going to match those of the direct function. But you don't have that here.
No, I don't have that. Go ahead.
So here you assume that the dimension of f is smaller than d. So can you just fix the dimension of that? You assume subject to the dimension of the function of the function to peak is just as a number d, and then you fix that dimension, and then you want to maximize the beta. I remember.
So you mean you change the dimensional function instead of inequality constraint to a equality constraint?
Yeah, no. So the objective function is just some. The first term depends on the dimension, and the second term is something beta. Is that right? The objective function.
So you're looking at a regularized problem, or?
No, just maybe the previous page.
I mean, we can talk this offline later. This is going to get complicated. Okay. So I don't have global optimal solution here. This is the probability error false alarm plot against the probability of detection. And the red curve is the Hoffman test if applied blindly to the problem. And if you happen to find the best, so if you, here I'm looking at the exponential family, the anomalous behavior lies in exponential family of dimension 12. So if I use dimension 12 and assume I have oracle tell me what's the best one, then I have the green curve, which is better than the Hoffman test just because I get better term before the error exponent. Okay, but if I restrict my dimension further and I use my heuristic, this is the performance I get for the dimension 4. Okay, so you get even better than the mismatch test with no mismatch. But if you are not careful, but you look at higher D, then you get worst case. That's partly because I don't have global optimal solution with my algorithm. So what I covered in this talk is first the finite sample performance of the symptotic optimal Hofting test degrees when the number of size alphabet is large. Okay, that's basically the variance issue, or that appears up in convergence analysis. And the mismatch test is proposed to address this issue, and its good performance depends crucially, as we already seen in this plot, on the choice of features. And we have a partially answer to this feature extraction technique, but we don't have a global algorithm. We don't have a algorithm with good performance guarantee. So what's ongoing work is we are working on algorithm looking at nuclear norm or other heuristic, which we can derive a performance guarantee. And the next thing is we have already extended this mismatch test to Markov processes, but we are looking at two hidden Markov model and general station process. Yes.
How come the one with no mismatch is worse than like some of the mismatch tests?
Good question. It's because because I'm looking at small number of samples, and here I think I use 40 here, but it doesn't make sense when I say 40. But what's the reason that this is better than here is the term before the error exponent is better than this d equal to 12.
Yeah, but that's exponential.
Right. Yeah, this will be worse than the green one if you look at number of samples increases. But usually with many application, you're not lucky to have a lot of samples. Okay. That's a question. Okay. That's conclude my talk. Thank you. Yes.
Sorry to bother, just one more question. Why did you basically collapse or approximate the Kullback-Leibler? Maybe the problem comes from the fact that you shouldn't be using Kullback-Leibler or any relaxation or amplification of Kullback-Leibler, but use something like from the work of Good and Turing, who have an adaptation of Kullback-Leibler divergence for large sample sets, for large alphabet, sorry, for large alphabet.
Good Turing.
So if you start with a different definition of your, so you don't look at the Kullback-Leibler or you don't look at the Hefting test, you look at the different type of test, then maybe you can get some things even with this relaxation that are more or better or more
Trackable.
appropriate for large alphabet sizes. And not go with the assumption that Kullback-Leibler is the best choice for dealing with large alphabet sizes and then trying to tweak it to the choice of the function.
Thank you.
Yeah.
No, thank you. That's a good point. Thanks.
Okay, let's thank our speaker.
Thank you.